Morning, everybody. So to get started today, I did get a question from someone, and I'm going to just go off, find some space here, and make a comment about this. The question was, could you go over the first and second derivative tests? So the first thing I think we'll do is we'll just what does the derivative tell you? The first derivative. It tells you what? The instantaneous slope. And if it's positive, that tells you the curve is increasing. If it's negative, that tells you the curve is decreasing. And if it's zero, it tells you we either have a max or a min. So any problem where you're told to maximize or to optimize or to minimize, you're going to approach with the first derivative. So if you want to maximize or optimize something, you're going to look for when the first derivative is zero. And if I ask you a question, what are the intervals this curve increases or decreases? You're going to what? Find, first of all, where is it zero? And then that breaks it up into the two parts, and then just do a test interval on each side. The second derivative, okay. Okay, all of a sudden we have a freeze here. Let's see. Well, we'll figure out what's going on here. All of a sudden I can't get the pen to work. But the second derivative tells you concavity. So when you take the second derivative, you should be able to determine second derivative. And that tells you concavity. And when you have a positive, it tells you concave up. When you have a negative, it tells you concave down. And when you have a zero, you have what's called a point of inflection. So if you were asked to find the intervals of concavity for a particular function, you would go ahead and find the first and the second derivative, and you would set the second derivative equal to zero, because the points of inflection are the dividing lines between concave up and concave down. Then you would go on either side of your points of inflection, and you would do a test value, second derivative, see if it's concave up or concave down, and then determine your intervals. So that's kind of a summary of the first and second derivative. And I think that's what the person was looking for. Okay? Now, what do you want to go through? What kind of questions do you want to look at to get ready for the test? So I don't know, I did some questions yesterday in the second section that I didn't do in the first section. So maybe I don't, honestly, I didn't keep track of that. So okay, I got a message here. Thank you. Let's see. Where are we here? email. Okay, sorry about this. Okay, so it's a separate question. I don't have to worry about it now. Okay, we did number 6 yesterday. I think we did number 13, and we did number 28, and I think we looked at 38. Those are all problems I think we looked at in class. I don't know which section it was. Somebody asked me about 89. Somebody respond. Was that 8 o'clock yesterday? Anybody? That was not our group. Thank you. Okay, so maybe we just take a look at this. Okay, now I did this problem differently than the book. Okay, but here's the idea. Find the length of the longest pipe that can be carried around a right-angled corner at the intersection of two corridors. One of them's 4 feet wide and the other one's 6 feet wide. So in other words, you got this straight piece of pipe in black here, and the question is, when will it fit around the corner without gouging the walls? So it's a hallway. You got a 4-foot hallway here. I didn't draw it to scale. You got a 6-foot hallway down here. So how long of a pipe can we get around the corner? Obviously, if the pipe is too long, you're not going to make it. Now, one thing that it doesn't talk about is you could raise one end and lower one end, and that would give you a little extra length, but let's not deal with that. That would be a third dimension. So my reasoning was, okay, when this pipe's at a 45-degree angle, you're going to do your best, and here's why. Because if you tip this pipe, let's say, on an angle like this, where it's tipped more severely, then I think you can see, just look at this side of the pipe over on the left side here. This black piece is obviously longer than this red piece because it goes over, it goes into the corner more. So what I'm saying is, hey, when it's in 45-degree angle, it's going to get the maximum. The same is true down here. This piece of pipe is longer than that one. So what I did is I made two 45-degree angles. Here's the first one, 4, 4. And you can find the hypotenuse. The hypotenuse, if you use the Pythagorean theorem, comes out to 4 times the square root of 2. And on the other one, you've got a 6, 6 situation. And the hypotenuse of that is 6 times the square root of 2. And if you add the two together, that'll give you the total length of the pipe. You should get 10 times the square root of 2. Square root of 2 is 1.4. So this is actually what, 14 point something? Yeah, it's something like 14.1. Okay, so now the book took a different approach. The book said, they went ahead and set up an ordered pair, and they said, all right, let's have the origin be the corner of the room. Let me make this a little bigger. So let's have the origin be the corner of the room, and let's have this corner that we're going around be 4, 6. And then this point will be 0. The point up here. The point up here. That'll be 0, y, and this will be x, 0. And then you set up the slope and you work. Anyway, notice they got the same answer, 14.05. So I took a different approach to it. Actually, mine, it's kind of interesting because my approach didn't actually make use of any calculus. But so anyway, there was a problem that some of you that you didn't see yesterday because I did it in the second section. I believe we did a box problem. Would you be able to do another problem concerning A box with maximum size? Sure, we can make one up. Okay. Let's just come over here. Do you want to make it up, or do you want me to? All right, I'll just make it up. Let's say we have, this time we have, I'm going to change the width of my pen here. Well, here, let's do this over again. Let's make this a little bit bigger. Let's make it black. Okay. So again, we have a square sheet of aluminum. And let's say this time it's 15 inches on the side. And the question is, you know, if we cut out square corners, then, you know, you'd have this, if you cut the corners out, then you'll be able to fold up the sides and make a box. So let's call those X and X. So what can we do? What size would be best to cut out? I mean, if we cut out nothing, the box doesn't have any sides and it has a volume of 0. If we cut out too much, like 7.5 inches out of each corner, then the bottom won't be left and we'll have no bottom times a really good height. Well, anything times 0 is 0. So somewhere in between, obviously, is the correct answer. So we set up a formula for volume. So what's the bottom of this box going to be for a dimension? It's 15 minus x minus x. So in other words, it's 15 minus 2x. And that's both the length and the width, correct? Okay. And then the height will be, it'll just be that x dimension, right? So there's basically our raw volume formula. Okay. So let's multiply. 15 times 15 is 225. 15 times negative 2x is negative 30x. Another negative 30x is you take negative 2x times 15. And negative 2x plus negative 2x is positive 4x squared. And all of that's still multiplied by x. Okay, 4x. Now I'm going to put it in descending order. 4x squared times x is 4x cubed. Minus 60x times x is minus 60x squared. Plus 225x. Okay, so there's our volume. Now, the whole idea is maximize this, which means this is perfect time for our first derivative. So v prime equals 12x squared minus 120x plus 225. Can't write what I speak. So 12x squared minus 120x plus 225. And now, of course, the whole concept is set that derivative equal to 0. So the first thing we're going to try is, can we do some factoring here? And it's not looking real great, is it? At least not for a common factor. We could take out a 5. Yeah, no 2 is going to work, so we're kind of stuck there. So the question is, can we factor this? Well, let's see. Let's at least give it a shot. So 12x squared has a lot of combinations. We could have 4x and 3x. You could have 6x and 2x. So let's just try a 4x and a 3x. So that would equal 12x squared. All right.
You can take out a 3 to make it easier.
What's that?
You can take out a 3 to make it easier.
Oh, it is. 3 does go in there? You're right. Thank you. So let's do that. That'll make it a lot easier. I just got a message. I will check it in a minute. So if we take out a 3, does that look right? Boy, and 73 is not friendly. So it looks like we're not going to be able to factor this.
Shouldn't it be 75?
Yep, thank you. So let's see, can we do something else with that? Well, if we go 2x and 2x, then 75 could be 25 and 3. It could be 15 times 5. That would be 30x and 10x. That looks like it's going to work. Okay, and we need a negative. So negative, let me double check. So negative 30x and negative 10x, that works. Okay. So set each factor equal to 0. And all of a sudden, my mouse died again. Yeah, all of a sudden, okay, let me try reloading here. Hang on a second. Now let's see if we can get this thing. There we go. So now we can set each factor equal to 0. We can't set 3 equal to 0. So 2x equals 15. X equals 15 halves. 7.5. That's garbage. Why? Because if you cut 7.5 out of each corner, you will have no bottom left. Okay, so that's, even though algebraically that's correct, we're going to reject that. So there it is. 2.5 inches is the ideal for what to cut out of that. So there's another box problem. Another request. Everybody's had a look at that. I'm just trying to look through and see if there's anything else I went through in the second class that I didn't go through with the first. I don't think so. Just flash the priorities up there again. Could we do number 42? Okay. Number 42. So let's go to the assignment. There's number 42. Okay. Oh, yeah. So anyway, let's look at the directions while I have it up. Find the points of inflection and discuss the concavity. So this is one of those where what? Where we need to do a second derivative. Okay. So concavity, points of inflection. Okay. All right. So if we want to take the derivative of the tangent, how do we do that? Secant squared, right? So, and we want to do it on the interval from 0 through 2 pi. Okay? So, get my pen. So, f prime of x equals the secant squared of x over 4. Okay? And then we have a what, a chain rule? I mean, this is like 1/4 x, so we have to multiply that by 1/4. Okay, and just keep the interval in mind. And then how do you take the derivative of the secant squared? Well, so for the second derivative, we need to first of all think of it as what? The secant. So we got, I'm going to put this 1/4 in the front. 1/4 times the secant squared. Well, that's not what I wanted to do. 1/4 times the secant of x over 4 squared. Okay, so now when I haven't done the derivative yet. That I shouldn't have. Let me get this out of there. Okay, so this is still a function, the first derivative. Now, as we endeavor to take the second derivative, we have to do the power rule. 2 times 1/4 is 1/2 times the secant of x over 4. Okay, well, what's the derivative of the secant? Secant tangent. So, hang on. Having a little problems here. The secant tangent of x over 4. And then we have a chain rule there. X over 4, again, is 1/4 x, and the derivative of that is 1/4. So we have times 1/4. So we have 1/8 times the secant times the tangent of x over 4. And now the question is, when is that equal to 0? Well, we can multiply both sides by 8, and that takes care of this 1/8. Okay. I got to think through this. When you take the secant tangent, that's the secant. Okay, let me think through this. Secant tangent. That should be secant. Yeah, let me rewrite that. That should be 0 equals secant x over 4 times tangent x over 4. Okay. So we got two things that could equal 0. This one and this one. So when can the secant of x over 4 be 0? Well, the secant's the reciprocal of the cosine, right? And when the secant could be 0, that means the cosine is undefined. Yeah, not that 0 is the reciprocal of undefined, but so when will the cosine of an angle hang on a minute. I gotta just think here. Secant of x over 4, when will that be 0? It never will be. And the reason is the cosine is never undefined. It's always between 1 and -1. So that doesn't give us anything. But let's look at the second part. When will the tangent be 0? Oh, the tangent could be 0 at what kind of angles? Let me get some space here. The tangent could be equal to 0 at 0 degrees. I know I haven't taken care of the x over 4 yet, but that could happen when it's 0, when it's 180, and any multiples thereof. What was the angle we were supposed to go up to? Is it 2 pi? So then that would be 360. Now, the problem is we've got what does x have to be equal to this? Well, x, when it's divided by 4, has to be 0 or 180 or 360. So our answer has to be multiplied basically by 4. Okay? So here are the x's. So this is x over 4. So x equals 0. And then this would be what? 720. And already we're over the top. We're past the requirement of 360. And then this would be what? 720. Yeah, well, this is going to be way too high. So basically it looks like our point of inflection is at 0. So 0 is the fence post. Now you just pick. Now the question is, when will this be concave up and concave down? So pick some angles that are less than 0. Like, for example, -30 degrees. Negative pi over 6. Okay, now go back to the second derivative, which is right here. And then go ahead and check the sign on either side, and then you can tell if it's concave up or concave down. So that would be the approach on number 42. Whoops. There we go. Also number 8 on page 262. Okay, number 8 on page 262. 262. Number 8. Oh, yeah. The sum of the first number squared and the second number. Okay. Actually, I have that one on here, I think. No, maybe I don't. Okay, let's do that one. So here's number 6. No, that's not right either. There it is. Here it is. Yeah, okay, so I must have done this during the second class. Here's number 8 on page 262. So the first thing you know is that there are two numbers, and they're both positive. And the question is, so I'm calling them generically X and Y. The sum of the first one squared plus the second, X squared plus the second Y, is 54. And so now we just need to get another name for Y. So we solve this for Y. We subtract X squared from both sides. So now our first two numbers are, our two numbers are not X and Y, but X and 54 minus X squared. And now you can finally set the problem up. It says their product. Let me go back and look. Their product is a maximum. Okay. So, set up their product. X times 54 minus X squared equals our function. Multiply those out. 54X minus X cubed equals 0. So if we're going to maximize, we just need to think through the first derivative, right? And the first derivative would have to be 0 at a maximum point. So find the derivative. 54 minus 3x squared equals that derivative. Set the derivative equal to 0. Solve for x. And there she is. So when x equals 3 times the square root of 2, we would be at a maximum. Let's just take a look at that one in Desmos and just kind of confirm. So what do we got here? It's 54x minus x cubed is the function. We're looking for a max. We got to zoom out quite a bit before we, this is a typical cubic equation. And the question is, what's the max? So that would be at this point right there. And if you check, 3 times the square root of 2 should be 4.243. Here, let's just do that. 3 times the square root of 2. Yep, see how it equals. Well, here it's rounded off, but that's 4.23. So we were correct. So going back to the problem. Now, sometimes I don't remember if this book does this, but what they'll do sometimes is say, on the value of x where this thing is a maximum, what is the maximum? So then you could just come back to your function right here and crank out, plug in 3 times the square root of 2 for x in both cases, and that would be your maximum. On this problem, they didn't ask you that. It just says, find the two positive numbers. Okay, so I really have just a little bit more to do. I found the first number is, so let's just jot this in. So we found x is 3 times the square root of 2. And then 54 minus x squared. What happens when you square this? You square 3, you get 9. Square the square root of 2, you get 2. So this would be 18. 54 minus 18 is 36. So what are the two numbers? There they are. 3 times the square root of 2 and 36. And that answers, yeah, find two positive numbers. We have now done that. Yeah, thanks for the request. Any others you want to look at? If you think of any others, you can send them my way by email. I can answer you that way too, or text, whatever works best for you. Okay, then I think we're going to wrap it up. Anyone else? Any other questions? Okay, thank you. We'll see you tomorrow.